Hi class, and welcome to week 4. This week we're going to talk about exponents and polynomials and how we multiply and divide these two things. And these are going to be very useful tools for the rest of this course as well as any future courses in algebra that you're going to take. So let's start off by talking about exponents. Okay, so exponents, when we're talking about exponents, we're talking about this little number here. When we've got something, what we call x raised to the first power, like this, and that just is equal to x. X to the first power is x. X squared, you've probably heard of, and that's just x times x. If we have something that's x cubed or x to the third power, that's x times x times x. So on, where x here can be equal to any number we'd like. We can say we can have 4 to the 4th power, where that's 4 times 4 times 4 times 4, which is 256. So hopefully you're seeing the trend. It's very straightforward. Exponents are just basically how many times we multiply a number, or in this case, or a variable, by itself. So x to the first is x multiplied by itself one time, or really kind of nothing, or it's kind of a confusing one. But so most of these are fairly straightforward. But what about when it gets really confusing, where we have x to the 0 power? Well, that's we have to sort of choose what that equals, and it doesn't matter what the value of x is. It can be 100 to the 0th power, 1,000 to the 0th power, 5 billion, anything to the 0th power. All of these things are equal to 1. With the exception, and we're not going to really worry about this, with the exception of 0. We say that 0 raised to the 0th power is an undefined number. It's not really meaningful. So we'll ignore that case. But any other number, as long as it's not 0, raised to the 0th power is equal to 1. Okay? So it doesn't matter whether it's negative, anything. A fraction, a huge number, all of that raised to the 0 power is just equal to 1. Okay, so hopefully that's all fairly straightforward. You've probably seen that at some point in the past. So now let's talk a little bit about multiplying and dividing exponents. Okay, let's look at an example like this where we've got x cubed times x squared. Let's just write that out sort of longhand, where that's x times x times x times x times x. And if we just, get rid of the parentheses, and we see that that's 5 x's here all multiplied by each other, which gives us x to the 5th power. So what we can do is sort of take this example as being the prototypical example, and for any case where we've got an x to the m times x to the n, that simply equals x to the m plus n. Okay, so in this case we had x cubed times x squared equals x to the 3 plus 2, which is 5. Okay, so very straightforward. Okay, what about dividing? In this case, we've got x cubed over x squared. Let's just write that out again longhand. We see we've got x cubed over x squared, just like this. Well, 2 of those x's will just cancel, right? X divided by x is just 1. So we're just left with an overall, we've just got a single x value left, okay? So again, we'll take this as being sort of the rule of thumb, and we'll extrapolate to find a general case. And we've got this, anytime we've got an x over m divided by x over n, we're left with x to the m minus n. So in this example, m is equal to 3, n is equal to 2, which is just 1. 3 minus 2 is 1, which in this case, x to the 1st power is x. Okay? Hopefully that's all very straightforward, but it's helpful tools. Okay, let's start to go over some more properties. This is basically what the first couple of sections of the text go over, and I'm just going to state them. You can go over examples. They're fairly straightforward, though. Okay, so if we've got an example like x cubed inside a parentheses, all raised to the second power, or x cubed squared, basically. What that is x cubed times x cubed, right? Write that out longhand, and we've got, you can count them, 6 x's up here, which gives us x to the 6th power. And let's rewrite that as a rule. Anytime we have an x to the m raised to the nth power, we end up with x to the m times n. So we multiply m and n times each other. So in this case, 3 times 2 is 6, giving us x to the 6th power. Okay, good. Moving on, this is the distributive power property of exponents. So basically, if we have two numbers like x times y, all raised to the m power, that m will come inside and raise x to the m power times y to the m power. Similarly, if we were dividing two numbers, x divided by y, that power still distributes. We have x over m, or x to the m power divided by y to the m power. Okay, so exact same rule, it just looks different because now we're dividing, but it's the exact same rule. Another one that is very useful is the fact that we can rewrite 1 over x to the m as x to the minus m. So that negative in front of the m, right here, indicates that it's actually 1 over x to the m. So that's a very useful rule. And just as with any other number, if we had 1 over x to the minus m, that's just equal to x to the m. But that's just rewriting. Hopefully that should all be very common. You should be used to that from fractions. But it just starts to look a little funny now that we use variables and exponents. Okay. Scientific notation. This isn't going to be a huge issue in this class, but it is a very nice notation to be able to use, particularly if you ever deal with very large or very small numbers. Okay, and I'm going to sort of show this one just by showing examples, and hopefully you'll understand the rule, because I think it's a little weird to describe, but it's easy in practice. Okay, so in general, we're looking for a form where we have a, where a is some number between 0 and 10, okay, times, this is an x for multiplication, not a variable x, times 10 to the nth power, okay? So we want some number like a times 10 to the n, okay? Let's look at an example to make that more clear. Okay, so we've got a number like 1,000. Let's put this into scientific notation. What we do is basically we want to find an initial number a such that it's between 1 and 10, okay? And in this case, that's 1 times 10 to the 3. Where does this 3 come from? This is basically how many zeros we have after our number 1 here, okay? So, and we have 3 here, and if we were to count 1, 2, 3, this is how many zeros we have after our number 1, okay? Let's look at another example. It's slightly more complicated. 5,003,000. Okay, third time's charm. 5,300,000. Okay, so what does our A have to be? Our A will make it 5.3 because that's between 1 and 10. And now we have to figure out how many positions we have to move the decimal place. We count from where our decimal place is, so it's not after the 3, it's where the decimal place is going to be located. And we count 1, 2, 3, 4, 5, 6, which goes up here. Okay, so 5,300,000 can be represented as 5.3 times 10 to the 6th power. Good. Now let's look at one last one. Now we've got a number less than 0. So now it gets a little bit more confusing, but otherwise the same rules will apply. Now we've got 0.0015. So again, we want to get an a that's between 1 and 10. So, and without losing any information, we have 1.5 would be an example. And now we need to figure out how many numbers do we need to move our decimal place. Well, we count 1, 2, 3 to get us to that 1.5, which is right here. But, so we've got a 3 right here, but notice that there's a negative sign here. That tells us that we have a number now less than 0, or less than 1, okay? So this tells us that we move our decimal place, we should move this decimal place to the left 3 to end up with our original number here. So if we were to take 1.5 and move our decimal place over 1, 2, 3 to the left is what the negative sign tells us, then we would end up with our 0.0015. Hopefully that makes sense to you. Hopefully you've seen this at some point in the past. We're not going to do it a ton in this class, but it is a very helpful notation to use, especially, like I said, large and small numbers. Okay, now let's look at polynomials. You've actually probably seen these before in the past, probably. We even saw some a little bit in earlier chapters. It's easier just to show you a polynomial than to try to explain it. But basically, it's some number like this, a 5x cubed plus 3x plus 1. So what we mean by polynomial is we've actually got multiple variables in here, or rather multiple orders of variables here. Okay, so we've got a x cubed term, an x term, just an integer. So this is a polynomial. It gets more complicated. We can have one like this, 6x squared plus 2ab. Notice we have another variable in there, so we don't only have to have single variables, we can have multiple variables. Okay, so this is a polynomial as well. Here's another example. Countless examples of polynomials, but here you get the point of what it is. And I should even mention, technically, x is a polynomial. Okay. All right. Let's look at the example 5x cubed plus 3x plus 1, and let's get some of the nomenclature out of the way. Each term, and what I mean by term is I'm looking at like this. This is 5x cubed is a term within our polynomial. It has a coefficient of 5. Okay, so this is the coefficient of our term, and the coefficient is simply a number in front of your polynomial. Okay. You also have the degree of the term. So in this case, this is our degree 3, or our third degree term. One more thing is you'll see the polynomial itself, the entire equation, this entire thing given an order. And usually what we do here, what we always do here, is actually choose the highest order. So in this case, our polynomial has an order of 3, okay? And that's chosen by this highest order term. Okay, this equation right here would have an order of 2. We usually would, it doesn't matter which variable you describe it off of, but usually we choose the highest, so here's a squared, so it's a second order polynomial. Same thing with this, we've got a second order polynomial here as well. Good. Okay, so now how do we add and subtract them? Very straightforward. What we're actually going to do, so here's an example. What we're actually going to do is add or subtract this terms with the same degree. So I'm going to write that out such that that's clear, but if we're adding this polynomial to this polynomial, I'll just stack them. That actually looks like this, where we've got x squared plus 2x squared minus 4x plus 0x, because we do not have an x term in this polynomial, and 3 plus 5. So we just add straight down here. So x squared plus 2x squared is 3x squared. Negative 4x plus 0x is negative 4x. 3 plus 5 is 8. Okay, very straightforward. You just add terms with, you add the coefficient for same order terms. Let's look at subtraction. We're going to take these same two numbers, and now let's just subtract them. And again, the same thing. Adding and subtracting are exactly the same. So we just subtract same terms. So again, we go x squared minus 2x squared is negative 1x squared. Negative 4x minus 0x is still negative 4x. 3 minus 5 is negative 2. Very straightforward. Okay, what about multiplying polynomials? Multiplying polynomials, we can have something somewhat simple like this, where we've got 5x cubed all times 6x plus 1. And then what we want to do is actually multiply this 5x cubed times each one of the terms inside. So first we have 5x cubed times 6x plus 5x cubed times 1. Okay? So we've got two terms in here, great. And then we can just carry out that multiplication, and we get 30x to the fourth power, right? Because x cubed times x is x to the fourth. And here 5x cubed times 1 is 5x cubed. Let's look at a much more complicated example, or a slightly more complicated example. And this is multiplying two what are called binomials, because there's only two terms in there. And you'll see these a lot, particularly in later chapters, but I'm not going to give it any special names. Let's just go over this in general. So what we want to do here is multiply each term in the first polynomial by each term in the second polynomial. So first is 5x cubed times 6x. Then it's 5x cubed times 1 plus x times 6x plus x times 1. Okay? And if we had more terms, then we would end up with more terms in here. Do that multiplication. And good. I'm going to skip over that part. We're not going to worry about that too much. Okay. Division of a polynomial. I'm going to keep it very simple here. Let's just look at sort of a simple case like this, where we've got a mononomial, 5x to the fourth over another monomial, 3x. Okay? So here, we're going to treat the numbers and the variables separate. So 5 divided by 3 is simply 5/3, right? There's nothing, or it's 1.4, however you want to write that, doesn't matter. I'm going to keep it as a fraction, 5 over 3. And then we divide the two numbers, x to the fourth over x, and we remember from the first section that that gives us x to the 4 minus 1, which is 3. So we've got 5/3. So we have 5/3 over x to the 4 minus 1, which equals 5/3 times x cubed. Okay? Let's look at a slightly more complicated example. 5x cubed minus 6 all over another monomial, 3x. So here, the way we break this up, let's just break this up into two monomials being divided. And this you should know how to do from our first example. It gives us 5/3 over x squared minus 2 over x, okay, or 2 times x to the minus 1, however you choose. So that's all there is to it. This stuff is very straightforward. Go over the examples, and you'll have this down in no time.